Thank you very much for inviting me to speak. I've actually changed the whole talk that I'm giving today because there was a conference a few weeks ago in Samos, and a lot of people have attended both, so I thought I'd change it up a bit and talk about something else instead. So what I'm talking about today is diagrammatic Cherednik algebras, and I've put a little proviso at the top there because I think some people in the audience might object to the term Cherednik algebras, so you could call them weighted Schur algebras if you prefer. And I'm going to look at them over fields of arbitrary characteristic. And all the results in this talk are joint with Anton Cox of City University and Liron Speyer of Osaka. Okay, so in section 1, I'm going to talk about the Ariki-Koike algebra. So given a couple of natural numbers, we have a complex reflection group given by this reef product here. And I'm going to let lambda L1n denote the set of L multipartitions of n. Okay, where an L multipartition is just an L-tuple of partitions, and you sum over all the sizes, and you get n. And I've written it L1n because these are complex reflection groups of type L1n. So that's why that notation is there. Now, this algebra is semi-simple over the complex numbers, and its simple modules are called spect modules in this case, and they're indexed by these L multipartitions of n. So that's all very well and good. Now, the next slide, this next point here, I'm going to be interested in a deformation of this complex reflection group, and I've denoted it HNF kappa, and I've put the F in there just to, I really want to emphasize the field in this talk. So this algebra is generated by these relations, generated by these T's. Now T1 to TL here, oh, that's wrong. T1 to Tn minus 1, this should be, sorry. These correspond to the generators of the symmetric group in that reef product up there. And then the T0 corresponds to the generator of the cyclic group. And so this algebra, which is very well studied, has this presentation. And I'm going to use just this notation here. This is just a recollection here. So, and all I'm saying is that this algebra is a deformation of the group algebra of this complex reflection group. So the whole of this talk is going to be about the representation theory of these Ariki-Koike algebras here, there we go, for arbitrary values of these parameters, so parameter being E here and kappa, and over arbitrary fields. Okay. Now, so here's a new parameter which people don't see so often in talks about Ariki-Koike algebras, and it's going to be indexed by an L-tuple of integers. And I'm going to call this a weighting theta. Now, given any one of these little thetas, there's a corresponding subset of my set of multipartitions. And I'm going to denote this by capital theta, so it's just a subset. And these are called Uglov multipartitions. And these are going to be very interesting when we start looking at modular representation theory of these algebras, these Ariki-Koike algebras. Now, I said that I've got this important subset. I also inherit from this little theta here an ordering on the set of multipartitions. And I call it a theta dominance order because it depends on theta. Now, for theta, one of these weightings, these here, we're going to obtain a complete set of simple modules for my Ariki-Koike algebra, and I will denote these d lambda for lambda in theta. So for people who are familiar with the classical theory, there is one particular theta here which would give me this guy to be the set of Kleshchev multipartitions. But this is a more general framework that I'm trying to talk about. And now, for an arbitrary theta, what we want to do is understand how to write any of these spect modules from the previous slide in terms of this basis of simple characters here. And so these are the matrix that tells you how to pass from here to here is called the decomposition matrix, and this is what I'm going to be talking about today. So I'm now going to go through the combinatorics of these partitions using this weighting that I've been talking about. So we identify a partition with its Russian array. So if I take the partition, too firm, 2, 1 squared, I want to draw a picture, as symmetric group people do, and I'm going to draw it like this. So I'm going to draw the rows going this way, so that's 2, and then 1 squared going this way, so that's 2, 1 squared. And I've called this Russian. It's actually got a flip, so you could call it anti-Russian notation, but that seems a little bigoted, so let's not do that. Now, each box here has got a width, and I'm going to give it width L. So here, in this particular case, this is I'm in level L equal to 1, so this box has width 1 here. Great, so they all have width 1. Now, what's theta going to do? Theta is going to tell me where to put this first box. So if I project down onto the real line, I'm going to put this first box so that its x-coordinate is given by theta 1, because this is theta 1 tells me where to put the first partition. And then this L tells me that I can tell you where the x-coordinate of any of the other points are, just as a multiple of L. So here, this one has position -1 if I set theta to be 0. This one has position +1, and this one has position +2. Okay.
So you don't go through the diagonals of the square, but it's just it has a meaning? Or?
It does have a meaning, but I've actually tried to get rid of it for this talk, but this is just a habit. You have to actually slightly wonkyfy them, and the reason is that just so that you want, technically, I'm not going to go through it, but you want the x-coordinate to uniquely do the point, so you just give it a tiny little rotation. Not exactly, 45 plus epsilon, but literally epsilon. Okay, so that's my pictures. So here's an example. So here, L is equal to 1, N is 3, and theta is 0, just like there. So here is the partition 3 with my notation. So I've sort of done these blue dashed boxes so you can sort of see around, but the black ones are the partition 3. Then this is the partition 2, 1, and this is the partition 1 cubed. And there's a dominance order, and I want to try and distill. The dominance order comes from theta. So here, people might be well aware that this is how you normally write down the dominance order for partitions, but what you should be getting from the visual is that the more boxes to the left, the more dominant the partition, which is quite clear in this example, and we'll see how it generalizes. Okay, so, I've lost my, there we go. So, I'm going to do another example now. So I'm going to let L equals 2, and there are two words here, Flutter and well separated, and we're just going to see what these mean. So here, I'm going to call this a Flutter ordering, and what's special about this ordering is that all these partitions are very close to each other. That's the point. So here, I'll call theta a Flutter weighting if theta I minus theta j is less than L for all I and j. So now remember, my boxes have got width L. So the point is that if I start at this blue box here, the closest box to its right is now the first orange box. And that's a Flutter ordering there that I've drawn. And here, this is a well-separated ordering for kind of obvious reasons. Now, a well-separated ordering is if they're really far apart. And in fact, I want them to be far apart so that the boxes in the first component really don't affect those in the second component at all. And the way I do that is that I insist that theta I minus theta j is always bigger than NL. So there are n boxes in total, and each of them have size width. Each of them has size L. So that will ensure that these guys are far apart. And we're going to do some more examples in a second. Now, the point about this theta is it's going to control all the combinatorics. In particular, I'm going to define theta controls this picture in two ways. The first of which we're going to go into in a little bit of detail, is it controls the dominance order. So I told you that the dominance order is going to be given by how far things are to the left. So of course, if I change the position of my multi-partitions, that's going to change the dominance order. So here we go. We write mu theta dominates lambda if the number of boxes in lambda to the left of any given point is strictly less than or equal to, less than or equal to, the number of boxes in mu to the left of that same point for all points along the real line. So it's just, the further the boxes are to the left, the more dominant. So here, for L is 2 and N is 3, so I've got 2 components and 3 boxes. I'm actually not interested in E and kappa. But here I've got theta to be 14, so that these guys are very far apart from each other. Now, what does the dominance order look like here? Well, this partition 3 is obviously the most dominant one, because it's got all 3 boxes going as far to the left as possible. Now, this next one here is the partition 2, 1, and he's quite dominant. He's fine. He's got all things in the first component, at least. And now I've made a bit of a jump here, but all I wanted to say is that here, all the boxes have moved a bit further to the left, so this is, again, less dominant. So here, the partition 3 empty set dominates 2, 1 empty set, which dominates 2, 1. And I'm now going to show you a different weighting in which this dominance order gets played around with, so that this ordering will change. So this is the well-separated weighting, remember? And this is the dominance ordering that Dimper, James, and Mathis use, and it's to do with cyclotomic Q-Schur algebras. And these weightings are called well-separated. Now here, I'm doing the Flutter ordering now. So look, L is 2, and I've picked theta to be 0, 1, so that these boxes are very close together in the 2 different components. And I've drawn a partition here, 3. Now, if you look at the x-coordinate of this orange box, it's given by 1, whereas the x-coordinate of the blue box there is given by 2. So 1 is to the left of 2, so we've changed the dominance ordering. And that's how these weightings change the structure of the algebras we're interested in. And they also do it in another way. This left-right malarkey can also be used to define a grading on the algebra. And so by playing around with the x-coordinates of the different components, we get to change the ordering on these algebras and the grading. So this is what we're interested in. And this dominance ordering, I'm accrediting it to Fodor, Leclerc, Okada, Thibon, and Welsh. And this is the Flutter acronym that you've heard earlier in the week. So we're going to call these Flutter weightings. It's not very attractive as an initialism, but we'll just stick with it. So I'm now going to talk about the algebras which are built out of this combinatorics. So these are called diagrammatic Cherednik algebras, and these are defined over any field via generators and relations. And these generators and relations look like the presentation of Kovanov and Lauder for KLR algebras. But they're more complicated, so I'm not going to draw them all on the board. And multiplication is given by putting diagrams on top of each other in a way that people are now quite familiar with in Lie theory. It is a finite dimensional graded cellular algebra, and here's the key thing of all the combinatorics I've been talking about. It's cellular with respect to this dominance order. So each different theta gives a different Cherednik algebra, which is why theta's in the brackets at the top. And they're all different and great. Now here's the key thing which makes these guys amazing. So, it's not this polytope. We want to study the Hecker algebra, the Ariki-Koike algebra. So we're going to start there. So here is the Hecker algebra, Hn kappa, which you notice doesn't depend on theta. So there's one single algebra, but for every one of these thetas, I get some diagrammatic Cherednik algebra up here. And this algebra controls the representation theory of this one. And it's given by, there is a idempotent, 1 omega, and all I have to do is take this algebra and hit it on both sides with this idempotent, and then I get the Hecker algebra. And this works over arbitrary fields, and this is the important thing. This is what makes these things awesome, because there are people also study categories O of rational Cherednik algebras, and over fields of characteristic 0, these also play the same role. So there is a KZ functor, which allows you to study this using this. And this has been very successfully exploited to learn a lot about these algebras. But this only works over fields of characteristic 0. Whereas the situation on the left-hand side of the board is characteristic free. And when you want to use if you want to study an algebra in terms of a quasi-hereditary cover, Schur-Wahl duality, these sort of things that people really like, you want to use Schur's idempotent. You just want to take the Schur algebra, the general linear group, hit it on both sides with an idempotent, and get the Hecker algebra, the symmetric group. And this is exactly what this algebra does. Except that it's graded and therefore better. But this is what makes this algebra excellent. And each time you do this, for any value of theta, you get the simple modules parameterized by the capital theta, which was, and we knew that these sort of already happened because of work of Ariki a long time ago, but the fact that there exists this algebra which always truncates down to there and always gives you these simple modules for any value of theta is very nice. And in particular, because it's an idempotent truncation functor, of course, the decomposition numbers of these algebras, so if these are the cell modules for this algebra and these are the simple modules, well, they pass through unchanged. So the decomposition matrix of the Ariki-Koike algebra appears as a submatrix of the decomposition matrix of the diagrammatic Cherednik algebra in arbitrary fields over arbitrary characteristics. Okay, so this is why I'm interested in these algebras, and now I'm going to spend the rest of the talk telling you about the kind of things you can prove using these very nice algebras. Okay, so we want to understand the decomposition matrices of these algebras over fields of arbitrary characteristic, and one of the first results in this direction for the symmetric group, well, not first, but it was a really good result, and it works over arbitrary fields, was due to Kleshchev, and here this is about one-box decomposition numbers. So I'm going to talk a little bit about this. So we want to understand Cherednik algebras over arbitrary fields, and hence understand the Ariki-Koike algebras. For the symmetric groups, Kleshchev calculated decomposition matrices, where two partitions differ only by moving a single node of a fixed residue. Now, this was generalized by Chuang, Miyachi, Tan, or quantized by those guys, and then generalized to cover moving lots of boxes of one fixed residue by Tan and Tio. Now, what's great about these decomposition numbers is that they only depend on the addable and removable R nodes that you're moving around. In particular, they do not depend on the quantum characteristic of your algebra, which was E, our little number E, or the size of the symmetric group you're interested in. So if you move 3 boxes from one position to another for S 1,000,000, it's the same as doing it for S 10, say. That's probably big enough. So that's a lovely result. And then you can actually generalize it slightly to if you pick 2 residues that aren't next to each other. If you have residue R, you're not allowed R plus or minus 1. Then you can generalize all this as well. So this is the state of the art for the symmetric group. Now, we want to generalize this result to diagrammatic Cherednik algebras and more general Ariki-Cauchy algebras. And we also want to explain this bizarre thing where it doesn't depend on the quantum characteristic or the number n. And we're going to do this by constructing isomorphisms between subquotients of our diagrammatic Cherednik algebras. And these isomorphisms are going to be independent of the level, L, in the Z over LZ, the rank, N, as I just said for the symmetric groups, the multi-charge kappa, the weighting, so it won't matter which Cherednik algebra I pick, these isomorphisms will always go through, and weirdly, the quantum characteristic. So you can, even in the classical Schur algebra case, we're going to get isomorphisms between subquotients of Schur algebras. Okay, well, we're going to get Morita equivalences between classical Schur algebras, between their subquotients, which don't depend on the quantum characteristic, which is quite weird. And of course, if we construct isomorphisms between subquotients, we're going to be able to deduce that the decomposition numbers and certain higher extension groups for these algebras are going to be preserved by this subquotient. So I'm going to go into this in proper detail and draw nice pictures in a moment. And we are also going to construct isomorphisms which lift Chuang and Tan's result to a structural level, but I'm actually not going to do that in this talk. Okay, so what's the story so far in this section? We have single residue decomposition numbers. Are independent of n and e, the quantum characteristic, and we're going to explain this and generalize. And again, everything we're going to do is going to work over arbitrary f. So I'm going to let gamma be a multi-partition which has no removable R nodes. So that's where I'm going to start from. And I'm going to let capital gamma, subscript m, denote the set of all multi-partitions which can be obtained from little gamma by adding m nodes of this fixed residue R. And this set is closed under the dominance ordering. So what does that mean? I'm going to take lambda L1n, which is a poset, and I'm going to be able to take the intersection. So I'm going to be able to truncate my algebra and then quotient out to get this set gamma m. And gamma m is going to have the property that if x and y belong to gamma m and x dominates y, x dominates z dominates y, then this implies that z also belongs to gamma m. So this is a nice kind of subquotient. This is a nice subquotient poset. And for general reasons, if you've got a quasi-hereditary algebra, passing from this big algebra to the small one is very nice, and it preserves a lot of nice properties. So that's what we're going to do. So how are we going to do it? Here is our partition gamma. So it's 7, 4, 1 cubed. And I've picked theta to be 0 just because. Now, I'm going to let my quantum characteristic be 4, and kappa, my multi-charge, be 1. And this means that I put the number 1 in the first box at the bottom, and then I go 1, 2, 3, 0, 1, 2, 3 up there, and along this way I go 1, 0, 3, 2, 1. And these are the residues of these boxes, and these appeared already this week. So this is just the residues of these boxes. I noticed that there's no boxes here which are removable of content 0. So let's fix R to be 0 and draw where I can add a 0 node. So here, all these x's, they mark points where I could put a 0 node on top of this gamma. So there's 4 places. So if I let gamma 2 be the all partitions which can be obtained by adding 2 boxes, this is going to have 4 choose 2 elements, so 6. And for example, one partition might be the one where I add the 2 boxes as far to the left as possible. So that would be 8, 5, 1 cubed. And the other one might be where I add the boxes as far to the right as possible. 7, 4, 2, 1 cubed. And actually, if you wanted to see why this is closed in the dominance ordering, this actually consists only of partitions which are between lambda and mu. Because, of course, there's a minimal and maximal way to add all these nodes. So it's just that intersection. OK. So this is one example. Now let's do another example. So now I'm going to let gamma be the bipartition. So here I've got 4, and then the next one is 3, 2. And this is a Flottwer dominance ordering. So here I've put these boxes very close together. I've picked theta to be 0, 1. And you see this red line cuts through this box here precisely because they're very close together. Now I'm going to pick E and kappa. So I'm going to let E equal 5 and kappa equal 0, 1 here. So I've put 0 in the first box at the bottom, then 1 in that first box at the top, and then I've just gone modulo 5 off in different directions to draw the nodes in there. I notice that there are no removable nodes of residue 4 here. So let's fix R to be 4. And I notice that there are actually 4 addable nodes here. So I've just put x's where they all belong. And here, gamma 2 bar has 6 elements, 4 choose 2. The maximum one is now adding, so here I add the boxes as far to the left as possible. And so I actually get 5 because I add in the first component, and then 4, 2 because I add in the second component. So that's this guy, and he's the most dominant partition. And then if I add the boxes as far to the right as possible now, they're again in different components, and this is a partition 4, 1, 3, 2, 1. Great. So here's my picture. I've drawn gamma. I've put ticks for where the boxes that I add for lambda, and crosses for the boxes which I add to get mu in both places. And the point is that the combinatorics above underlies an isomorphism between these subquotients labeled by these sets of partitions. So on the left, we have a Cherednik algebra with n equal to 11. So there are 2, 4, 6, 7, 8, 9 boxes, plus the 2 that I'm adding. So that's n is 11. Here, my weighting is theta 0, 1, and my kappa is 0, 1. On the right-hand side, I've got 16 boxes when you include the ones that I add, and theta is 0 and kappa is 1. But there is a isomorphism between these two subquotients of completely different Cherednik algebras. And under this isomorphism, you can, for example, deduce that the lambda bar mu bar that I mentioned before, where I've put lambda, the 2 ticks, mu the two crosses. This decomposition number is equal to this one on the right, where I've added boxes again to the right, these ticks, and here I've added boxes on that way. So you can clearly identify the posets just by where do you add boxes relative to each other, and then lambda and mu, it's just a matter of where you've ordered the boxes to be. Okay. So that was an example of something you can do with these Cherednik algebras. Now I'm going to talk about alcove geometries for these guys over fields of arbitrary characteristic. I've maybe raced a bit through that. I don't want to run out of material, so if anyone has any questions about Kleshchev decomposition numbers, feel free to ask them now if the post-it wasn't clear. T, sorry, so it's a graded algebra, so this decomposition number is 1, but if you add the grading in, then it's T to the 4, sorry. Yes? So I mean that here I've got, in my first algebra, E was 4. Is that right? No, here E is 5, and here E is 4. And these label subquotients of different Schur algebras, if you like, different Cherednik algebras, where in the first one, I've got a quantum characteristic equal to 5, and in the second one, I've got a quantum characteristic equal to 4, but they're still isomorphic, these subquotients, which is something you don't often see. Does that explain? No? So, I mean, if I wrote down... Okay, so alcove geometries. So over C, the decomposition numbers of these diagrammatic Cherednik algebras can be equated with coefficients in Uglov's Fock spaces, which I'm not going to go into. This was proven by Rouquier, Chan, Varigno, Levasseur. Once you interpret these diagrammatic Cherednik algebras as being Morita equivalent to what they're interested in. And then subsequent proofs by Ben Webster and Lesève have turned up as well. So because of this theorem, there are actually algorithms for computing these decomposition matrices over the characteristic zero fields. But nothing is known for positive characteristic, so let's try doing that. In particular, part of the level 1 phenomenon is that you can calculate decomposition numbers for fields of very large characteristic by Anderson-Janssen-Sergels results. And we would like to be able to come up with something similar for Cherednik algebra, diagrammatic Cherednik algebras. Okay, so I'm going to have to be quite specific in order to do anything, though. So I'm going to have to pick theta to be a Flottwer weighting. So remember, all this, if I want a Flottwer weighting, I need to pick L tuple of integers, which are between 0 and L, because that was the width of the boxes. So I want all the boxes to be really close together. So that's what my theta is doing. So that's going to be a Flottwer weighting. And now what I'm going to be interested in is a subset of all multi-partitions in which each component has at most h columns. So here's an example. So here, if I consider partitions of 40 into 4 components, so here there's 4 components, 1, 2, 3, 4. So that's the 4, 1, 40. Now, if I want them to have at most 3 columns in any given component, then the first number is always going to be less than 3. So that's all I'm saying. So all this set is talking about is multi-partitions with some restriction on the size of the first row. And of course, if I specialize L equals to 1, then this will be quite familiar to people as something that we do in Lie theory. We restrict the number of rows or columns, and we try to prove things. Now, what is nice about this case is that there's a nice quotient of the diagrammatic Cherednik algebra and its representation theory is entirely governed by this set. And we're going to look at this quotient. Now, this might seem a bit hard at the moment, but for example, if L is 1, we should know that the classical Schur algebra, its representation theory is governed by partitions with less than or equal to H columns, if it's GLN H. Oh, H rows. So that would be the classical Schur algebra, if that was my restriction. But I'm going to swap and instead consider H columns. So what I'm looking at is the Ringel dual of the classical Schur algebra of GLH, for H times H matrices. People don't normally use H, but I'm trying to emphasize the Coxeter number, hence the H. Okay, so we're going to look at this nice quotient category, which includes as an example the Ringel duals of the classical Schur algebras and generalizes it to higher levels. So, and we're going to have to, in order to get things to work out, we're going to have to pick kappa to be nice. And I can explain that later if people are interested in what nice means. But with this extra restriction, I'm going to be able to look at these nice quotients, these nice generalizations of the Ringel duals of classical Schur algebras, in terms of an alcove geometry of this type. So here, AH minus 1 is governing each component. So I've got L of these, L AH minus 1s, and it's inside a larger affine type A Weyl group. And I'm going to do this for my quantum characteristic greater than or equal to the Coxeter number of the bigger Weyl group. So examples, if L is 1, so if I fix L to be 1, I'm not going to get any multiplicities here. I'm just going to get one copy of AH minus 1 inside of AH minus 1 affine. And this is the parabolic geometry which controls the general linear group of H by H matrices. So it controls the classical Schur algebra and its Ringel dual. And I believe that if I set H equal to 1 and L to be arbitrary, then this is an non-parabolic affine geometry which controls the Kac-Moody algebra GL L hat over C. So what do these geometries look like? In the first case, which is L is equal to 1, let's do an example with H equal to 3. Well, here I draw triangles everywhere. And so this looks like the symmetric group on 3 letters. So the symmetric group on 3 letters is my parabolic, so that tells me that I'm going to work modulo this. So all I color in here, so it's this chunk that controls the representation theory of GLH, GL3. So here, it's 1/6 of the plane, which controls the representation theory for L is 1 and H is 3. And if I let H be 1 and L be 3, then I draw the same picture, but now there's no parabolic, so I'm going to color in the whole plane. And this whole plane labels representations of the, this algebra. And when you want to do things like compute decomposition numbers, you look at how this controls the representation theory. So these are the examples. They're distinct, obviously, and I'm going to look at something that is somewhere in between them and contains them both as examples. Okay. So the first thing is that if I take an alcove geometry, I get all these alcoves, and I can label them by elements of Weyl groups and reflect and stuff. And this comes with a natural ordering. And all I'm saying is that the ordering in these pictures down here, these alcove geometries, that ordering tells you the ordering on the structure of our Cherednik algebra. So that's the first thing you need if you're going to prove anything about in Lie theory. You need that you want a strong linkage principle. You want to understand that the representation theory of my algebra the ordering, at least, is controlled by the ordering on the alcove geometry. And I'm not going to explain what the ordering is, because the idea is just to get a feel of geometries control algebras. Now there's this classical result of Carter and Payne, which says that if I take two partitions and in my alcove geometry, suppose they are, so if I continue with my level 3 example here, so in, not level 3, but here we go. So suppose I'm doing H is 3 and the level is 1. Then the way we draw, the thing that controls the representation theory of SL3 is this diagram where I've got a 6 of the plane and I just tile it with triangles off to infinity. Now, a Carter-Payne pair is any pair which differs by a reflection through one hyperplane, where these two are separated by only one hyperplane in this direction. So that's a Carter-Payne pair. I have a Carter-Payne pair here, where these 2 points are given by reflecting in this wall. And I have more complicated ones, so I can also reflect through this wall. But again, the point is that there's only one hyperplane in each case which separates the two of them in this direction. So here I'm separated by 3 hyperplanes, but they're all in different directions, so that's okay. So these are all Carter-Payne pairs. And there's a classical result in this level 1 case, which says that if I take one of these Carter-Payne pairs, then I get a homomorphism between the cell modules, and this homomorphism is of degree given by some length function to do with my geometry. And there'll be more homomorphisms of smaller degree, but they're all strictly smaller degree. And this is a classical result in the level 1 case that dates back to a long time ago, maybe the 60s. And all I'm going to say is that when you take these more general geometries, it also generalizes. Okay, so we've got homomorphisms coming from this geometry. The geometry controls the ordering on the algebra. So this geometry is very related to these algebras. And if I fix my field to be the complex numbers, in fact, you can run your Kazhdan-Lusztig theory in any old geometry, and if you run it in this geometry, you're going to be able to calculate the decomposition numbers of these algebras, and they're simply the Kazhdan-Lusztig polynomials. And even better, is actually that you can interpret the basis of my algebra here as walks in this geometry, and then the whole Zirkel folding up points way of calculating decomposition numbers is simply a change of basis between the simples and the standards. So, in other words, proving this theorem was really easy, and normally it's not. Normally, people have to work very hard to prove the decomposition numbers of an algebra given by Kazhdan-Lusztig polynomials, and we essentially got it for free by just drawing nice pictures. And here's the bit where it gets sort of away from things. This was sort of already known. These decomposition numbers are known. It's sort of a different way of thinking about them, maybe. But the main point is that you can conjecture that because this picture works so like the classical case in level 1, and it's generally just follow your nose, generalize it, we conjecture that these decomposition numbers will also work in suitably large characteristics. Okay. So that is how these geometries control these diagrammatic Cherednik algebras. So finally, I'm going to draw some more pictures and just talk about ways of reducing the problem of calculating decomposition numbers for a larger algebra to a smaller algebra. And there were results in this direction due to Gordon James and James-Donkin for the level 1 case, and I'm going to look at the higher level cases. So what Gordon James and James-Donkin do is they take a partition, and they want to consider ways of chopping it up into smaller partitions. So if I was looking at GLn's representation theory, and I had a partition of n, well, a partition of R into at most n pieces, what they would do is they would cut this partition halfway through. And so if this is lambda, if you could cut this partition, and if this was mu, and you could cut this partition at the same point, then they would be able to relate the representation, this decomposition number into, if this is lambda, this is the top part, this is lambda, the bottom part, this is mu, the top part above this cut, mu, the bottom part, then they would be able to prove things like d lambda mu is equal to d lambda top, mu top, so this decomposition number for a smaller algebra, times d lambda bottom, mu bottom, where this is another pair of partitions for a smaller algebra. So this is the kind of thing that they did in the 80s, and people have looked at since for homomorphisms and things. And this is the kind of stuff that they were interested in, and this is what we're going to try and do. Break up partitions into smaller pieces, and hence factorize problems about the representation theory. So here are two bipartitions. So here is a lambda, and here is a mu. So these are both bipartitions, because there's two parts. This first one, lambda here, is 11, 9, 7, 3 cubed, 2, 1 cubed. That's him. 9. Oh, there we go. 9, 7. And I want to draw a line here at the same point on both diagrams, and I want to cut this partition in half and this partition in half. So if I go to the next, what I've done is I've colored in. So here I've made this cut at this point, and now if I look, I go ooh, along there, down, up, and this is going to be 1/2 of the partition. Well, this bipartition. So this is pink. Everything in pink is a bipartition, and it's the right hand, we call it the 1/2 of this cut. And if you sum up the number of boxes in here plus here, you'll find that it's actually the same as the number of boxes in here plus here. So I can cut both partitions, and the right-hand side of this cut, which we call it because it's sticking out at the right, for lambda and mu has the same number of boxes. Now, if I want to see what the left-hand side of this cut is, I'm going to do the same thing. So I've put the cut here, so this is where I start, and I just draw around there. And this line goes down to here, so that's why these boxes here are in as well. All of these things are to the left of this cut. And obviously, I'm going to need to include some number of extra boxes, because otherwise it's not a partition. Now, on the other side, I've done the same thing. So this was my cut for lambda, and this is my cut for mu. I've drawn a line down here, and then I've just included all the boxes which are to the left of this line, and the minimum number of boxes for this to be a partition in both cases. So I've cut my partition into a pink bit and a yellow bit. So if we just enjoy that for a second. And now you're probably going to be able to guess, given this sad sketch here, what I'm going to do next. I'm going to say that this yellow bit here, we've just dropped the coloring, because we're, there you go, that's lambda left. This is the left part of lambda. This is the left part of mu. So if I go back, oh, I went forwards. So left part of lambda, left part of mu, left part of lambda, left part of mu. And now for the right part of lambda, right part of mu. Oh. So I've cut it into two parts. And the point is that the decomposition numbers will factorize along these two parts. Now, you can do this for more general pairs of multi-partitions. And if you do that, then you'll get a nice theorem. Let lambda and mu be a pair of multi-partitions of n, and A be a point along the real line. So A is the point at which I'm going to draw my big line here. So the point A, which goes through my multi-partition. if I do a cut and it through this multi-partition at this point, I call it a theta cut because, of course, it depends on theta as to the number of boxes which are at any given point. So this is going to cut my partition into a left bit and a right bit. And as I said, we can factorize these graded decomposition numbers by using this picture. And moreover, we can in fact factorize higher extension groups between these two modules in terms of a tensor product here, where these are smaller algebras. So look here, this is here's my smaller Cherednik algebra, so NL is the size of this partition, and NR is the size of that partition. So I've factorized this larger extension group into this sum over tensor products from the smaller. And in GLN case, this was all done by James-Donkin and independently by Sinead Lyle and Andrew Mathis. I believe Sinead and Matt Fayers also did the HOM case. So this is sort of our analog for higher levels. So I think that's all I wanted to say.